Okay, we're going to continue on with Unit 3. These are recovery machines. If you look at these, we have two recovery machines. This one here on the left is a very good one. I personally own one of these. We also have these in the lab. This is an air-cooled recovery machine. It works extremely well. I won't say it's bulletproof, but it's a very good recovery machine. I will show you how to set this up in the lab. But this is probably, I would say, it's probably one of the very more popular ones that I have out there. They also have different manufacturers. Here's another one here, and I'm not sure who makes this particular recovery machine, but it's, I believe that's a Robinair, but I cannot tell from this picture. And you will find this on page 63 of your textbook. Okay, here's where things get kind of dicey. Look at all those different refrigerants here. Notice that you have drums, you have disposable bottles, you have these huge cylinders. You also have these cylinders that are very similar to your oxyacetylene and weld gas cylinders. And notice they all have different colors, okay? Obviously, some refrigerants are no longer around, such as R12, that's long gone. R22, that was phased out in 2020. Now, of course, that was over a year ago. And you have all these different refrigerants in these bottles. Okay, up until fairly recently, we had a color for every refrigerant that was out there in current use for refrigeration air conditioning systems. Now they have decided that we're going to label and go to one standard color. So going forward, you're going to see a lot of bottles that are painted the same color, and they're going to be labeled. I would say probably the only exception to that rule would be your disposable cylinders, such as these. And of course, here's some of those refrigerants that are no longer available: R12. R22 is becoming a little harder to find. R502, long gone. 134A, there's plenty of that stuff. Here's the one I like here, R500. That is a early blend. Basically, it mimicked R12 and R22, sort of. Basically, it was used in air conditioning equipment manufactured from Carrier Corporation. In fact, it was called Carine 500 when this refrigerant first came out. Now, if you look at this orange barrel up here, this probably contains R11. And this refrigerant typically is sold in drums, typically 100, 200-pound drums like this. You had a bung that you would have to unscrew. You put a special fitting here, and you charge up your chillers with this. And of course, there's 1/3. These refrigerants right here, I would say, are probably going to use in centrifugal large water chillers. Over here, you might recognize these cans. These are kind of like the ones you buy over at your automotive trade store. And typically, they're going to use special fittings to charge your automotive air conditioning. Up until recently, R134A, which has been in use in automotive from 1994 until a couple of years ago, has now been replaced with a refrigerant called R1234A. I do not know the characteristics of that particular refrigerant, but it's quite interesting. Another thing I want to point out on these refrigerant bottles here are non-refillable. In other words, once the gas is gone, you are supposed to recover what is in the remainder of these cylinders, and you are supposed to take and punch a hole in the cylinder once it's reached a vacuum state of 10 inches or more, and dispose of these cylinders as scrap metal, okay? These bottles obviously are refillable and replaceable. Occasionally, these bottles have to be recertified by the manufacturer to certify that the safety plug and all that stuff is in good working order. Okay, this is basically a piece of refrigerant copper line set. Typically, you're going to have your, on your mini splits, you're going to utilize you're going to insulate both the liquid line as well as the suction line. Typically on your air conditioning system, you're just going to insulate the large line, the suction line going back to the compressor. One of the things that you're going to find now in the new systems is we are utilizing a special covering, which is kind of a rubber product, which contains a Velcro type jacket that you are going to literally encapsulate the outside of this insulation. One of the problems that we've had because of our severe sun heat exposure in the summertime, the so-called UV tape that we were utilizing to take and protect this Rubitex insulation didn't do its job. Typically that tape would deteriorate, and once that tape deteriorated, of course, this insulation would deteriorate over time. And typically 3 to 5 years after you put the system in brand new, you're probably going to find yourself back at the customer's house replacing it. So the building codes now mandate you utilize this product, which basically consists of a rubber jacketed Velcro fastening type covering to insulate the refrigerant lines. Okay, basically this is a diagram just showing you the refrigerator. Shows that heat transfers through the walls and insulation because of the warmer room temperature, okay? So basically, the better the insulation, the ability to keep the heat out. That applies to building construction as well. As far as walk-in boxes, insulation makes a huge difference. If you have leaks, you're going to be using your air conditioning refrigeration plant more and more. If you have gaskets that leak, if the door is propped open, you are going to create more load. Basically, you're going to run the compressor over a longer period of time. So heat transfer through the walls and insulation because of the warm room temperature of 70 degrees. So you will get some heat transfer even with the box closed. It's well insulated. It should be minimal. All right. And we looked at this picture previously in the other slide set. You have your warm air replaces the cold air inside the refrigerator. Cold air falls out because it's heavier. Okay, the direction of refrigerant flow and refrigeration cycle. There we have the liquid line. Should be solid liquid. This refrigerant should not have what they call flash gas, a mixture of gas bubbles and liquid. It should be a solid liquid column to that thermal expansion valve, which is the metering device. Then of course you have the entrance to the evaporator coil. And then you're going to have a thermal bulb, which is going to be mounted on the outside of this evaporator coil. Notice that the bulb is mounted in a horizontal position. It is not recommended that bulb be mounted vertically. In other words, up and down. Should always be mounted horizontally. It should be clamped in place, okay? Needs to be clamped in place with copper strapping preferably, because that transfers the heat better, and utilize like a brass, utilize a brass fastening system. And I'm talking about a machine screw and nut and washer to clamp this thing down. They also make stainless steel clamps that will clamp this bulb to this suction line. Irregardless, this bulb needs to be insulated right here. Has to be insulated with, like, say, a press tight tape in order to keep the outside heat from interfering with it, because that'll give you a false temperature. And this valve is going to open and close based on the temperature. But if the surrounding temperature hits that bulb, that will influence the opening and closing of this valve and not give you the correct amount of superheat going back to the compressor. And once again, refrigerant leaving this evaporator coil should go back as a vapor, low pressure vapor. It should not be liquid. And then the compressor is going to change the refrigerant from a low pressure vapor state to a high pressure vapor state so that the heat can be given up in the condenser. Okay, here we have a rotary compressor inside an air conditioning unit. Notice that we have a discharge line in the form of a loop. This loop basically is a shock absorber on this air conditioner. So basically absorbs some of the pulsating that comes out of this compressor. And then of course the refrigerant in this case is now entering the top row of the outdoor condenser. This is a window unit. Evaporator fan inside a walk-in box. We talked about that previously. Okay, here we have the, we talked about this diagram about how this refrigerant cycle works. We showed earlier how the fan motor is going to distribute air over the evaporator coil. And notice that the refrigerant coming, the refrigerant going from the compressor is going to be 200 degrees. So this will be the condenser, the high side of the system. Notice that we are utilizing R410A, which is currently the refrigerant we're going to use in most air conditioning systems now. You'll still find a lot of old R22 systems out there because there's millions of units in the United States that still contain the old refrigerant, which is R410A. It was a good refrigerant, R22 I'm talking about now, and it's an HCFC refrigerant, which has been taken out of production as of January 1st, 2020. So now you're going to be utilizing 410A or other refrigerants in place of R22. Is R22 still available? Absolutely. You're going to pay a steep price for it. We talked about here the enthalpy diagram. Okay, here we have a water temperatures, and then we have the absolute pressure, then we have the boiling point. Let me see if I can find that diagram in the book, see what the reference to that is. I believe that diagram, give me 1 minute. Okay, that diagram can be found on page 44, which is figure 3.7. This is the boiling point of water. The temperature at which the water will boil at a specific pressure can be found on this temperature pressure chart. And this is just for water only. By the way, water is considered a refrigerant. Okay, here we have a typical condensing unit. Notice that you have the compressor, which is wrapped down here in a sound blanket in order to minimize sound transmission. This insulated jacket, like I said, it cuts the sound down and the sweat prevention around the compressor. Up here you have a run capacitor. This is a split run capacitor. One part of it feeds the condenser fan motor, the other part feeds the compressor. This is also equipped with what they call a hard start kit. That's what this capacitor over here, this is a start capacitor. There will be a relay, which is probably up here, and that relay is going to take this start capacitor out of the circuit as soon as the compressor comes up to speed. Then notice that this has got a PC board, and of course you have your thermostat connections. And what I find rather interesting, even though you have contactors here, notice that the connections from the outside power basically are going to wire nuts instead of to the contactor directly. This is a typical small condensing unit that we're going to see on refrigeration systems. Typically your reach-in boxes, your different types of refrigeration appliances in a restaurant or kitchen. Notice over here, this is the suction line. And the reason why I say that is because notice that Armaflex / rubber insulated tubing is wrapped around it. And notice that this is coiled. The reason why that copper suction line is coiled so that this unit can be slid out for service. You have your access valves over here. You can mount your gauge manifold. You're going to have your low side, you're going to have your high side. This is the liquid receiver. condenser fan motor, condenser, very typical. And over here we have a start capacitor to assist in the operation of this compressor. One of the ways to look for leaks, especially on refrigerant bottles, as well as refrigeration systems, as well as welding equipment, is to use soap bubbles. Now, I need to make a statement here regarding the use of soap bubbles on looking on oxygen bottles as an example. This is an acetylene bottle, so I'm not terribly concerned. But if this leak detector, which contains petroleum products, is applied to a leaking oxygen bottle, it may cause an explosion. And the reason is that the oxygen will react with the petroleum chemical products of that soap solution and possibly create a negative reaction, which could lead up to an explosion. So please be careful when you're utilizing a gas leak detector containing petroleum products. I typically, when I am looking for leaks, I will utilize chemical like Simple Green. As a matter of fact, Simple Green works extremely well, and it is doesn't contain petroleum products, and it does the same job. Here's something that should be put in an antique store. This is when I got into the business 45 plus years ago. This was a tool of choice for looking for leaks. The idea was you would have this chamber, which you would light with a match or a striker, and you would have a flame burning beyond this copper reactor plate. This is a sniffer tube, and this sniffer tube would basically take and draw leaking refrigerant into this tube, and through this venturi, it would basically react with the flame inside. The color of the flame would determine the intensity of the leak. There was one problem with this. You would never want to use this type of leak detector in a room that was full of refrigerant, because basically refrigerant in an open flame condition will turn that refrigerant, cause it to break down. The chemical composition will change the phosgene gas, which you may or may not know is deadly, and create some real problems. You will not see these utilized today at all. Pretty much, I would say this is a museum piece if there ever was one. Okay, this is a leak detector. This is an electronic leak detector. This could be a halogen specific. It could be an ultra. I will give you more information on that just one second. That particular leak detector, I used to have, I have a similar brand that's made by Field Piece. I like it very well. I believe we have some in the lab tool crib where you guys can utilize this product for looking for leaks. Basically, you have a off-on switch. These lights are going to light up, and the intensity of the leak is going to cause this display to go from a single beep all the way over, and it'll chirp in. This is your sniffer tube. You're going to have usually a cotton protection on this tube, which is going to, what it's going to do is when this thing senses a refrigerant leak, it is going to be drawn through this and cause it'll cause to mix with the electronics in here, and it'll tell you if it's a strong leak, a weak leak, and that'll be displayed on these lights here. IFCON makes a very good leak detector. They're not cheap. That one there is probably in the $600 price range, would be my guess at this point. Does it work? Absolutely. This particular leak detector, you'll find it on page 60 of your textbook. And like I said, works very, very well. Okay, these are the scroll plates on a scroll compressor. Basically, you're going to have your fixed plate and you're going to have your orbiting scroll. The idea is you're going to take the gas. It's going to be a mixing between the orbiting over the fixed, and the refrigerant is going to be compressed and discharged out through the center. The nice thing about a scroll compressor is you don't have valve plates per se. These do an excellent job of compressing refrigerant. But remember, all these compressors are designed to pump refrigerant vapor, not liquid. Please remember that. Very, very important. Okay, here you have a PT chart. This is going to show you the classification, this A1, A2, A3. They now have come out with a new replacement chart, which is going to allow some flammable refrigerants to be utilized in refrigeration and some air conditioning applications. So this safety designation chart has been updated. And basically what's going to happen is you guys are going to have to get specific training on these new refrigerants, which have, I should say, petroleum products that are flammable. As an example, propane. Believe it or not, that can be used as a refrigerant. Butane could be utilized as a part of a refrigerant mixture. The problem is, of course, if you have a match nearby, the stuff tends to light up and explode. So there are some issues with that. Then you're going to have your ANS and your ASHRAE designations, such as your R11, R12, and all these different refrigerants. Right now, we're dealing with about 85 different refrigerants out in the field. So you're going to do what I expect you to memorize it? Absolutely not. You need to just get your phone out with a app on there, and then basically you can determine what refrigerant is utilized on a system. And as long as we're talking about refrigerants, let me just make one thing very, very clear. Because of the fact there are so many different alternative refrigerants out in the field today, one of the things you got to be extremely aware of is this. The refrigerants can replace R22, R12, that kind of thing. But the newer refrigerants don't have the heat capacity that the original refrigerant had. As an example, if I take a system which contained R22, which leaked out through no fault of anybody's except something broke on the unit, of course, R22 is through the roof as far as pricing goes. So could I put in 407C to replace it? Sure, you could, as long as the other refrigerant is out. The point I want to make is simply this. Do not, and I repeat, do not mix refrigerants. If you got a unit that's low on charge, if you got an R22 unit that's not completely flat, but it needs a couple pounds of R22 to bring it up to snuff, use R22. Don't use another alternative refrigerant in conjunction with the refrigerant that's in there, because what you are doing is creating a chemical cocktail, which is going to create a lot of problems if you do that. And these are the chemicals that are utilized in these refrigerants over here. And notice when you come out here, look at 401, you got several, in this case, R22, 152, 124. Then you come down here to, let's just take 404. Look at all the refrigerants involved here. You have to literally become a chemist in order to figure out the chemical composition here. PT chart. You guys should have one of these in your wallet, or better yet, download an app. There's different apps out there, and it'll give you your saturation. It'll give you your, it's going to give you the pressure, and it's going to give you the what they call the saturation temperature. So as an example, let's just take 134A. Now notice that these numbers reflect the fact below atmospheric pressure. Once we get up to atmospheric pressure, notice that these are now positive numbers instead of printed red. So be aware that some of these refrigerants are going to show a negative or a vacuum at a certain area of the system. Now here's that new refrigerant that's utilized in automotives, R1234YF. And it's a little bit different than 134A that it replaced. So, and once again, you cannot mix refrigerants. You're buying a new car, probably you're going to have 1234YF refrigerant in there instead of R134A. You need to check the labels. Make sure you are dealing with the right refrigerant. Air conditioning, same suit. You need to check the label. Make sure you're using the right refrigerant. If you don't know, There are different ways you can copy down numbers, model serial, and get in touch with the manufacturer or the representative, and they'll be able to help you tell you what refrigerant that unit was originally charged with. And under no circumstances do you mix refrigerants. If it's rated for R22, stick with R22, okay? R410A are just the same thing. 410A and R22 do not mix. It's either one or the other, gentlemen. You can't mix them. Okay, the icebox principle. Now notice here we have a solid block of ice, and of course the ice is below 32 degrees. As this ice evaporates, that ice is going to take and leave the refrigerator in a form of condensation, very cold condensation. Now, the heat that is in this product is going to be absorbed by this block of ice. Once the heat is absorbed by that block of ice, that heat is going to melt the ice into the in the form of H2O and then exit the refrigerator through the drain line. Now, another process you may or may not have heard of is called sublimation. And basically, this is what sublimation is. Basically, the refrigerant changes state, but it changes state. It doesn't go from a solid to a liquid to a gas. It goes from, like, in this case, from sublimation, it goes from a solid to a vapor. An example of this would be CO, carbon dioxide. Carbon dioxide, you basically, you can take and freeze it. Carbon dioxide basically is going to absorb heat at a very cold temperature. And as the heat attacks the ice, what is left is vapor. You don't have no liquid. So you basically, in a sublimation process, you're going to go from a solid to a vapor with no liquid. Please remember that. All right, the refrigerator showing where the heat leaks in, and the refrigerator components to pump the heat out. Typically, the refrigerator is going to have a condenser coil underneath here. And by the way, domestic refrigerators have condenser coils. A lot of people today do not know that. And guess what happens to that condenser coil? It gets dirty, and that condenser coil is supposed to reject all the heat out of the food product stored inside. But if the condenser coil is loaded up with dirt, it's not going to be able to do the job. And when that happens, you have problems. And the ability to maintain temperatures over a long period of time are going to be called into question because the condenser coil underneath here is plugged up. What's the solution? It's very simple. It's called maintenance. You get in there with a vacuum cleaner, air hose, blow all that dirt and dust out. Of course, make sure you protect surrounding areas because your kitchen might get a little dirty in the process. But the condenser coils need to be cleaned out periodically. If they're not cleaned out, the result is your temperatures over time will go up. Your compressor runtime is going to go up. And over time, you are going to cause early failure of the compressor because of excessive heat buildup or dirt buildup on the condenser coil. Okay, here we have a situation where we're boiling water. Okay, when we boil water, basically at atmospheric pressure, the temperature is 212 degrees. When we boil water, we change it from a liquid to a vapor, okay? And notice this is at 14.6 or 29.92 at sea level. Best way I can describe that. Okay, room air conditioning here. Here we have a situation where we're utilizing in this case here, it appears to be we're utilizing chill water, okay? So basically what is happening is we're bringing water from a chiller into this evaporator coil, and we're probably gonna bring this water in at 38, 40 degrees, whatever. And then of course the room air is gonna hit this evaporator coil. It's gonna give up its heat to the cold or chill water. That in turn is gonna raise the chill water temperature up at least 10 degrees. So basically, if you got chill water coming in, as an example, 46 degrees, it should be leaving this coil at, in this case here, it should be leaving this coil at about 55, 56 degrees. Okay, here we have an interesting situation here. If I was to take this water and put it in a glass seal tight arrangement here, basically, and put this dome where this water is inside. Now, the water right now is 70 degrees, but look what's happening to the water inside this sealed dome, and I apply a vacuum, in this case, 0.739 inches of vacuum. What happens to the water? Starts boiling off. That's the reason why we utilize vacuum pumps in refrigeration air conditioning service. We want the moisture inside an air conditioning refrigeration system to boil off. The liquid line filter dryer does a very good job of removing a lot of that moisture. However, the vacuum pump does a better job. The vacuum pump, if the system is leak tight, is going to indicate that your system is leak free. When I take and put a new system in, I always use a micron gauge to tell if the system is properly sealed up. Once again, inside that jar, it is 70 degrees. Notice the water is boiling because we placed it in a vacuum. Okay, now we have a situation where we take and raise the temperature of the water inside this saucepan, 250 degrees. So basically it's above the boiling point. So as the water boils off, of course, we create a positive pressure inside this pan. Okay, 5,000 feet above sea level, atmospheric pressure, we're at 24.92 inches of mercury. Water boils. In this case, look what happens to the boiling temperature. It drops. So the higher you go above sea level, you basically can lower the temperature of the water boiling point. So instead of 212 degrees at 5,000 feet, notice that the temperature drops by 2003. If you go even higher, then obviously the temperature that you boil water is going to be less. Here we have a centrifugal compressor. We have the inlet suction elbow, and notice the refrigerant is going to hit that wheel through the center, and the wheel is going to spin typically at 12 to 15,000 RPM, very fast. And as that refrigerant is thrown around this volute area of the centrifugal, that is going to cause a compression effect, raise the pressure, raise the temperature of the refrigerant. And then, of course, the outlet of this compressor is going to discharge refrigerant vapor, superheated vapor into the condenser, where the heat that was picked up in the evaporator, of course, is going to be let go. Here we have another picture of the scroll compressor, which we had in our earlier presentation regarding scroll compressors. Here we have a picture of the rotary compressor. Notice that you have like an eccentric situation here where that rotor moves in an offset. You have a spring-loaded blade, which keeps a seal-tight arrangement between the suction and discharge. Here we have a reciprocating compressor, low pressure vapor refrigerant goes in, and of course you have a reed valve, suction flapper valve opens, allowing refrigerant vapor to go in. As the compressor piston reaches the bottom, then of course it goes up, and then it'll push that refrigerant out through the discharge flapper valve. And of course, we raise the temperature, we raise the pressure of this refrigerant vapor, not liquid. And by doing that, we're going to be able to give up the heat of the refrigerant that was absorbed in the evaporator to the condenser. Another picture of a reciprocating compressor showing the up and down motion, and shows you the crankshaft circular motion. Here's an R410A system. Notice that we have, I believe this is the Okay, I'm sorry, I just got distracted here for a second. So basically we have the metering device. We showed this earlier in the previous presentation showing the metering refrigerant going through this either a capillary tube or a piston. And notice that we have a 75% liquid, 25% vapor going through the evaporator coil. Is liquid about halfway up, and then the refrigerant, as it picks up the heat, is going to boil off. It's going to change from a liquid back to a vapor, and that in turn is going to take and boil off in the form of, how do I say this? The refrigerant is going to take and boil off into a low pressure, low temperature vapor, which can now go to the compressor and be, the refrigerant can be compressed into a high temperature, high pressure vapor. So the heat that's picked up in the evaporator side of this refrigeration system is going to be given up to the condenser. Notice that refrigerant we're utilizing in this diagram is R410A. Okay, here we have the room air, which is 75 degrees. And notice the coil, all the refrigerator air conditioning systems are designed for 40 degrees. It's considered a high temperature system, but 40 degrees is the magic number here. Here we have a pressure enthalpy chart, and it doesn't say which refrigerant this is. I believe this one right here, yeah, it doesn't actually spell out which refrigerant this applies to, but this is an example of a pressure, temperature, enthalpy chart that you can plot an air conditioning refrigeration system. And here's where the plotting takes place right here. Notice that you got A, B, C, D, E. You can actually find out where the compressor, you can find out where the evaporator, you can find out the metering device, all this stuff right here within this block. Once again, here's another pressure temperature chart and showing the plotting, and this would be a different refrigerant. In this case here, many different types of refrigerant out here. And basically, we can take and plot this system by utilizing a chart. Unless you understand how these charts work, you're going to struggle with them. When I got into the air conditioning business 45 years ago, basically one of the problems I had was learning this chart because it was not explained to me. I had to take classes just on interpreting these charts. Will you use these in a service operation? I would say the answer is no, but you need to understand how a refrigeration air conditioning system is designed, what it is capable of doing, and what it's not capable of doing. So by plotting this, we have the ability to figure out if that system is working properly or not. Another diagram, notice that we have the angle isotherms down here, enthalpy, pressure. I'm not going to spend much time on this. Okay, now we have an interesting situation here. If you take a look at this diagram here, we see a pump down at the bottom of this hill or mountain, whatever you want to call it, okay? And that pump is taking a suction on the water, and basically, what are we doing here? When we look at this illustration, what does this indicate of anything at all? Is this of any significance or not? Any idea what we're trying to show you here? If you look on page 42 of your textbook under figure 3.5, power is required to pump the water uphill. The same is true for pumping heat up the temperature scale from the interior of a 35-degree refrigerator to a 70-degree room. Same idea applies here. This is found on page 42 of your textbook. Okay, here we have refrigerant, which has where we have the dividing line basically between the high side and the low side. We have an orifice metering device, which basically is a calibrated hole here. Notice that the subcooled liquid is going to go through this opening right here. Is going to go through this opening, and that in turn is going to cause a pressure drop. When we create a pressure drop, now this solid, high pressure, high temperature liquid now goes to partial liquid at 75%, and then a partial vapor at this point. And at this point, this refrigerant is now going to be utilized to absorb heat in the evaporator coil. And look at the pressure drop. We're going from 446 psig to 120.5 psig. Quite a huge change. By creating that pressure drop, we are now able to change the function of this refrigerant in order for that refrigerant to absorb heat in the evaporator coil. Okay, this is an example of a leak detection kit where we inject a chemical into the circulating refrigerant liquid in the system. The idea behind this is we can utilize UV lights, a special type of light to find a leak in a system. So by injecting the chemical, utilizing these the product inside here, then we basically inject this chemical, and then they furnish you with a special UV light where you can determine where the leak is at. I was involved many years ago with the US Navy. They were trying to figure out how to take and find leaks safely on chillers aboard submarines, because on submarines, typically submarines deploy below the waterline, obviously. And in order for that to happen, you have special equipment which produces oxygen and, of course, removes the carbon dioxide. Well, the problem is if you have refrigerants spilling out, that could create some toxic environments for the sailors in a submarine when it's submerged. So one of the ideas we came up with was utilizing this liquid chemical dye, which had no effect on the atmospheric conditions of a submerged submarine. And this turned out to be a very good idea. By injecting this chemical along with the refrigerant, we are circulating. Now we can use this light, pinpoint the leak, and of course, find it and fix it. Okay, here we have another pressure enthalpy diagram, and we are just showing what is happening at this particular point. We're going to plot this. I'm not going to spend a lot of time on this, other than to call your attention that these charts are quite useful for determining what the system is doing at a given point. So just be aware, these are there to help you plot and determine what this system is doing at a given point. And I believe this particular, if you want more information, see if I can find it for you. This is going to be on page 64. This is the reference point used for measuring the heat content as it is saturated liquid at 40 degrees, or I should say at minus 40 degrees Fahrenheit. Over here on the following page, on page 65, this is the quality of the saturated R410 at 60 degrees Fahrenheit with a heat content of 45 degrees per pound, is 10% vapor and 90% liquid. Once again, we can plot what this system is doing. In this diagram, now we have a complete plot, which you're going to find, I believe an example of that's going to be on page 67 of your textbook. This is a refrigeration cycle plotted on a pressure enthalpy chart. So this is plotting the entire refrigeration cycle utilizing the chart. On this diagram, which is also, let's see, I believe that's on page, okay, this one's going to be on page 68. This is the compressor inlet point, point D on the pressure enthalpy chart. And this one here is going to be, let's see here. Okay, this is going to be found on page 69. This is the compressor discharge temperature, which is determined from the constant temperature line. This diagram here is going to be found on page 68. This is the net refrigeration effect, which is abbreviated NRE. and the total heat of rejection on this particular plot diagram for refrigeration cycle. This is something I learned a lot many years ago. Are you going to apply it out in the field? Probably not. I will just say you need to know the fundamentals in order to understand the refrigeration process, in this case, the net refrigeration effect of an air conditioning refrigeration system. Okay, in this diagram, which we talked about earlier, this is an example of a room air conditioner. Of course, you got the evaporator inside here, the blower here, then you have the compressor over here, along with the condenser fan motor, the condenser. Basically, what happens to the refrigerant going through this cycle, we talked about this earlier. Heat's going to obviously leak into the house. If you got good insulation, you can retard the heat buildup inside the house. If you have poor insulation, bottom line is you're going to need a bigger air conditioner to remove all that heat. And one thing I should talk about right now very quickly is this. When you size up equipment, there's a lot of misinformation out there. A lot of people think their square footage should tell you how much, how big your equipment needs to be to remove heat. That is not necessarily true. You need to really do what they call a heat load calculation, heat loss, and heat gain. Heat gain is going to be for air conditioning. Heat loss is going to be for heating. The idea is we want to figure out how much insulation is in your house. We want to figure out how many people are in your house, how many heat producing appliances in your house, and where the heat is coming from. If you stop the heat from coming in, you know, you could have a 3,000 square foot house, and if it's properly sealed and insulated, you could probably get away with a 2.5 ton air conditioning system instead of a 5 or a 7 ton. So one of the things I'm going to tell you now, a lot of houses, older houses, are poorly insulated, and they require larger equipment just to keep up with the heat that's infiltrating the building. How do you stop it? Replace the windows, fix the doors, stop the leaks, use thermal imaging equipment, and you can take and you stop the leaks infiltrating the house. You can cut down the size of the air conditioning and, of course, your electric bill. Okay. Now, this shows R410A in a cylinder. Now, look at the temperatures and pressures. This is very, 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 very important to understand what is going on. You can actually predict what is going to happen to the temperature or the pressure by having the surrounding temperature. If you know the temperature, you should be able to predict what the pressure of that refrigerant is going to be. In this case, it's R410A, which we utilize in air conditioning equipment currently. Notice at 35 degrees, look at the pressure, 107.3 psig. Now we surround this refrigerant bottle of R410A at 75 degrees. We should have on our gauge 217.6 psig at 75 degrees. Now, if we go up to 100, look what happens to the pressure. It goes up to 317.1. So what are we saying? We can actually predict what that refrigerant pressure is going to be based on the surrounding temperature. If you measure the surrounding temperature of the bottle, provided the bottle is properly labeled, you should be able to predict that refrigerant without the use of a PT chart, well, to use a chart, and you should be able to figure out where your pressure should be. So, does temperature have an effect on the pressure of the refrigerant? Yes, it does. Please remember that. And I am trying to see if there is a picture in your textbook on this, which I have not found. Give me 1 second. It's on page 47 of your textbook, figure 3.14, and basically shows the saturation of 410A at 35 degrees, which is 107.3 psig. The pressure is saturated R410A at 75 degrees should be about 217.6. The pressure of the saturated R410A at 100 degrees is going to be 317.1. Here we have a screw compressor. Notice they have the refrigerant. It's going to enter up here through the lobes. You have the inlet going through, inlet of refrigerant vapor going through here, and as it goes through these lobes, it is going to compress that refrigerant in this screw vortex arrangement. And of course, the outlet pressure is going to exit out the backside. You're going to see screw compressors primarily on air conditioning equipment, typically above 50 tons in capacity. And here we talked about this chart earlier based on the, let me find that again for you. And I believe this particular chart is located on page 55 under figure 3.31. This is a typical R410A air conditioning system showing the temperatures, airflow. Red indicates the warm, hot refrigerant. Blue indicates the cold refrigerant. Another pressure temperature enthalpy diagram. We talked about this earlier today, but you can find these references to this pressure temperature chart. I believe this is on page 66 under figure 3.43. And this will show you what happens to the refrigerant, what different lines represent in that pressure temperature diagram chart, which we also used to call a Moliere diagram, believe it or not. Okay, here we have an outdoor condensing unit on the roof. And what's interesting, this is figure 3.51 on page 71. It's a medium temperature R134A refrigeration system showing operating temperatures and pressures. So of course, here you've got the compressor, here you got the condenser coil. And of course, these are the temperatures. Here's the sight glass next to the evaporator. Then you've got the TXV. And of course, we have 32% liquid, 68% liquid going through the evaporator coil. And as we leave that, of course, we end up going through the low side of the system. And that low side of the system is going to be, remember, refrigerant going back to the compressor is going to be a vapor, not liquid. And then this just shows what happened as that refrigerant hits the compressor. It is compressed. Obviously, we increase the temperature. We also increase the pressure. And that in turn creates the condensing temperature in order to give up the heat, which was picked up down here. Okay, this diagram here, I believe, is on page 67 under 3.45. The condenser outlet is identified by the point of the expansion device line crossing the saturated liquid line on the left side of the pressure enthalpy chart. Okay, in this diagram here, which is right above, that is going to be figure 3.44. This is the refrigeration cycle plotted on a pressure enthalpy chart. And on this chart here, this is going to be, I believe this is the net refrigeration effect, NRE, total heat of rejection chart. Now, this is something I really love. The particular item that I have is not made by this company, Ampro. It is made by another company. I'd be glad to demonstrate that to you in the lab if you ask. But what is nice, notice that you have a pair of headphones. And on the particular instrument I got, it's called AccuTrack. It's got a sniffing tube. And basically, you're going to wear these headphones and you're going to use sound waves to find a leak. This does work. It works extremely well. And what I love about it, but the microphone is so sensitive. By changing the sound of the leak versus the background, you can determine where the leak is exactly at. I like this instrument because it pinpoints where the leak is at. Then you follow up with the soap bubbles or another electronic leak detector to confirm. I found lots of leaks utilizing this equipment. It works extremely well. And with that, I believe that's the end of this lecture for Unit 3, the pictorial side. If you have any questions, please contact me by email, and I'll be happy to answer questions, or please ask me in class during the lab period, and I'll be able to assist you with the different things you saw in this presentation. Thank you for your attention. Have a good day.